Okay, so in this section, which is 4.3, we are learning how to solve separable differential equations. So separable differential equations are a special type of differential equation. All right, so where we have dy dx is equal to f of xy in a separable differential equation. F of xy has a certain form. F of xy either looks like f of x times g of y, or f of xy looks like f of x over g of y, or f of xy looks like g of y over f of x. So basically, I can separate my problem. And we're going to use differentials. So we're going to use the theory of differentials. Okay, so these problems require quick, little, simple integrations. So here's an example. This is the one first, so I'm give you some examples. The first one is going to be the one that we did. Dy dx is equal to y. Okay, so here I can see that g of y is just y, and f of x is just 1. There really is no function of x there, it's just 1. So now I am going to write this as dy. I'm going to bring the y down here. And I'm going to bring the dx up here. Kind of like I cross multiplied in a sense. Okay. So I divided by y on both sides and I multiplied by dx on both sides. Everybody okay with that? That's real simple. Now I'm going to throw in an integral. So now I'm going to throw in an integral and I'm going to get the integral of dy over y is equal to the integral of dx. So now I'm integrating both sides. Okay, now what is the integral of dy over y? It's the same as the integral of dx over x or du over u.
ln of y.
Okay, so it's going to be ln of y. I'm not going to worry about the absolute value because the absolute value will be taken care of in the constant. Okay. I get a plus c. Let me call that c1. So I get a constant on the left side when I integrate. Okay, what's the integral of dx? X. Plus another constant, c2. So I'm just going to take that other constant and make it the log of y is equal to x plus one constant minus another constant. So I'm just going to get rid of those and write it as the log of y is equal to x plus one constant. No point in carrying along two constants So now you know whenever we integrate both sides, we can assume the constant is on one side. Okay, how do I get to that y? It's a logarithm. What's its inverse function of logarithm?
Is it exponential?
It is the exponential. So now I can do e to the natural log of y is equal to e to the x plus a constant. Okay, so both of them are in the exponent. Okay, let me draw a little line just so you can see. They are both up there in the exponent. Okay, e to the log of y, they're inverse functions. So this is just going to give me y. And then this is e to the x times e to a constant. Now, e to a constant is just a constant. I'm going to call that a. So therefore, I get y is equal to a e to the x. So that is the general solution of the differential equation. Now, suppose you're given that y of the log of 2 is equal to 4. So that's my initial condition. So I get this as an initial condition. So if you're given an initial condition, you must solve for any constants. So now I have y. I can see when x is equal to the natural log of 2, y is equal to 4. So I'm going to go up to my solution and put 4 is equal to a times e. And in the place of x, I'm going to put the natural log of 2. So that gives me 4 is equal to a, e to the natural log, again, they're inverse functions. So I just get 2. So that tells me a is 2. So now I have a unique solution, y is equal to 2 e to the x. That is my unique solution, or what we call a particular solution. Okay. Here's another one. Number 2. Solve dy dx is equal to 1 plus y times e to the x. And the assumption is y is greater than -1. So I don't give you an initial condition. Okay. So now I get dy over 1 plus y is equal to e to the x dx. It's separable. I have a function of y times a function of x. So I can split it up. It's separable. Okay, the left-hand side integrates to, so now I get the integral of dy over 1 plus y is equal to the integral of e to the x dx. So when I integrate the left-hand side, I get the log of 1 plus y. I know I get a constant, but I'm going to put it on the other side. I get e to the x plus a constant. And since I didn't give you a value, initial value, I don't know how to solve that exactly. So that answer is just like it is. It is just that. Okay. This is what we call implicit function of y. In other words, I didn't solve for y. Okay. I'm going to do one more, and then you guys are going to do one. Y times x plus 1 times y prime is equal to x times y squared plus 1. Now, don't let the y prime trip you up. That is still dy dx. So I have y times x plus 1 dy dx is equal to x times y squared plus 1. Okay. Put all the x's on one side, all the y's on another side. I'm going to get y over, this is separable, y squared plus 1 is equal to x over x plus 1. And this one is dy, and this one, other one is dx. Okay, so now I want to integrate them. The integral of y over y squared plus 1 dy is the integral of x over x plus 1. Now, this x plus 1, that one's a little tough. Okay, so the left-hand side is fairly easy. U is equal to y squared plus 1. Du is ty, 2y. So I need to be able to integrate. So the left-hand side, I'm pretty cool with. I know that the left-hand side is going to integrate to 1/2 the natural log of the absolute value of y squared plus 1. That's the left-hand side. Okay, if you do the integral. The right-hand side is tricky because they have the same power. Remember, when the power of the numerator is the same or larger, we have to do long division. So I have to do x plus 1 into x. Okay. All right, so x goes into x one time. I'm going to get x plus 1. There's a silent 0 here. I subtract and I get -1. So now I know that x over x plus 1 is simply 1 minus 1 over x plus 1. So that's what the right-hand side becomes. So then when I do the integral of the right-hand side, I just get the integral of 1 minus 1 over x plus 1 dx. And that's going to give me x minus the natural log of x plus 1. Okay. Plus a constant. So now I get 1/2 the natural log. Y squared plus 1 is positive, so I don't need x absolute values, is equal to x minus the natural log of the absolute value of x plus 1 plus a constant. And that is my answer. Okay. Okay. So here's a problem that's an application. It's called Newton's law of cooling. Okay. And I actually like Newton's law of cooling because it always describes so many things for me. It says H is the temperature of an object. Well, let's let T be the temperature of an object. So T equals the temperature of an object. And T naught is the temperature of the surrounding medium. Okay, so Newton's law of cooling says that the rate of change of temperature of an object, so this is the rate of change of a temperature, it's a lot of ofs. The rate of change of the temperature of an object is proportional to the difference between the temperature of the object and its surrounding medium. So this is proportional to the temperature of the, so this is the difference in temperature of the object and its surrounding medium. Okay, so the way we write it is dt is equal to minus K times T minus T naught. And here K should be positive. Let me write the temperature of the surrounding medium as TS as opposed to T naught, because T naught could be something else. So we're going to use TS. Okay. So K is the heat diffusivity, the diffusivity of heat. Okay. And then T at 0, T0, and that is the initial temperature of the object. Fast. Okay, so if the temperature, if I'm hotter than, okay, does anybody know which way heat flows? Hot to cold or cold to hot?
No, hot to cold.
Heat flows from hot to cold. Okay. That is why if you are 98.6 degrees and you walk outside and it's 110 degrees, you feel like you're going to burn up. Okay, because all that heat is trying to jump into your body. If you are 98.6 degrees and you walk outside and it's 12 degrees, heat is leaving your body, trying to warm up the earth so you feel like you're freezing. Okay, so this particular thing makes sense. When T is bigger than TS, that's positive, which means this value is negative. So the rate of change of T is decreasing. So you are losing temperature. If you are hotter than the surrounding medium, if you are colder than the surrounding medium, okay, so T minus TS is negative. The T is you're hotter than the surrounding medium. Then this K is positive. So now this whole thing becomes positive. And no, yes. And so now that means you start to increase in heat because your medium is hotter than you. Okay, so how do you solve this problem? All right, well, we're going to solve this problem just like we just solved the other one. So we're going to take dt over, always leave that constant with up, don't put the constant in the denominator, just leave it there. T minus S, TS is equal to negative K dt. Okay, so I moved T minus TS to the denominator. So on the left-hand side, I have only capital T's. On the right-hand side, I have only small t's, which is time. Okay, integrate the left-hand side. So we're going to have the log of the absolute value of T minus TS is equal to minus K times T plus a constant. So now we're making an exponential of it. So we get e to the log of absolute value of T minus TS is equal to negative K T, E to the negative KT plus a constant. On the left-hand side, I get T minus TS is equal to E, I'll leave it in absolute value for a moment, E to the negative KT times E to the C. Now this E to the C, I did the same thing I did before. I'm going to make that an A. So now I get T minus TS is A E to the negative KT. So now I have T is equal to TS plus A E to the negative KT. Now here's the thing. I gave you an initial condition. I told you that when little t is 0, capital T is your initial temperature of the object. So I get T naught is equal to TS plus, I'm going to put in 0, so I get A. So now I know A is T naught minus TS. So therefore I get T of T is now equal to TS plus T naught minus TS E to the minus KT. So when T is 0, I just get T naught. And as you can see, as T gets bigger and as T goes to infinity, the whole thing goes to 0, and I eventually get that this thing becomes the temperature of the surrounding medium. Okay. So here's a problem. I took roll already, right? Yeah, I did. Okay, here's the problem. A hard-boiled egg at 98 degrees Celsius. So 98 degrees Celsius. Ooh, that's hot. Is put in a sink of 18 degrees Celsius water. After 5 minutes, the egg's temperature is 38 degrees Celsius. Assuming that the water has not warmed appreciably. What a word. In other words, we don't have to wear. How much longer will it take the egg to reach 20 degrees Celsius? Okay. How about? Okay, any questions so far? All right, so somebody tell me some values that they know. What do you get from this problem? I can tell you I see T0. I also see TS. Here, right there. Top envelope. Y'all gonna wait me out till I have to do this on, nope, y'all gonna do this tomorrow. I will let Mr. Samuel finish this problem in recitation. We still have a few seconds left. Anybody want to give me T naught? What is T naught? Okay, I'll let Mr. Samuel finish it. Thank you, guys.